Thank you. Yeah, so I'm Jamie Sullivan, postdoc at MIT. For all of you who are here before this week, I've met most of you, but I'm going to talk a little bit about some work that we put out in May. Me working with Misha at MIT and Carol, who was also at MIT until recently, on looking at nonlinear bias for galaxies in stage-5 spectroscopic surveys, in particular focusing on these high-redshift galaxies. This is the new physics from galaxy clustering workshop. Before we can do the new physics with the galaxy clustering, we need to understand the new galaxy clustering. Oh, this work. Okay, great. But the most important thing I want to say comes from this slide. This is a photo that I took while just walking around up in the hills. I want to thank the organizers for allowing me to be here and participate and experience Florence, all the food and all the things that are fun to do. And there's still one more fun thing I want to do, which is to go see Galileo's middle finger. And it's in the usual orientation, oriented upwards. And if you want to do that, let me know, and we'll try and organize that sometime this week. It's down there somewhere, in the museum. Okay, anyways, back to galaxy clustering. So Noah, in a previous week, gave an overview of the stage-5 spectroscopic survey landscape when talking about some forecasts and how the galaxy clustering is going to come from these higher redshift star-forming galaxies. And this is going to be the future of large-scale structure for the next few decades. We've talked about this a few times, but and Satya talked a little bit about DESI-2, but DESI-2 and SPEC-S5 are going to be the efforts in the US, and then planned other efforts are the WST in Europe, and then in China, they've started building this MUST telescope, which is very similar to the SPEC-S5 plan. Going to high redshift, just as a little bit of a review, at higher redshift, of course, there's less nonlinear structure formation, so KNL has gone to larger values, and we're probing new volumes that we haven't seen before when mapping out cosmological modes. Downsides is that it's harder to detect these galaxies with a fixed amount of exposure time because they're at higher redshift, you're getting fewer photons in the flux, and that the galaxies are not as well understood as the galaxies that we're used to at low redshift. And when I say not well understood, I mean astrophysicists have looked at these galaxies and there have been small surveys, but there haven't been these large-scale surveys with these very strong statistics that allow us to constrain, for example, the nonlinear bias parameters. Okay. And I'm going to talk about that a little bit here. Noah mentioned these briefly, but there are two main types of star-forming galaxies at high redshift that we're going to be using for the galaxy clustering measurements going forward, kind of shown in this cartoon on the right here. The first are these Lyman alpha emitters, and these are galaxies that have a very strong Lyman alpha peak in the rest frame, and they are lower mass galaxies, and they have actually a pretty low bias. So this question kind of came up, I think, last week or the week before, of how much we're worried about nonlinear bias of very highly biased tracers, which naively could set the effective Kmax to be pretty low when doing galaxy clustering analyses. So that's kind of the question we were trying to address here. But naively for the Lyman alpha emitters, due to their low bias, you might not have this problem. And we'll see that's kind of the case. For Lyman break galaxies, shown in a cartoon here by this dashed or dotted line, these are galaxies that are higher mass in the higher stellar mass tail of the star-forming galaxy population. And they're selected via this decrement in color in the blue compared to the redder side of the spectrum. And okay, so those are the two main galaxy populations. And like I said before, the question we're trying to get a preliminary handle on is whether modeling the clustering will be hard due to the effective Kmax. And we tried to have a first step towards an answer here by using simulated galaxies, hydrodynamic simulations. There's an asterisk here, of course, because there's a lot of assumptions that go into the hydro galaxies that you may or may not believe, but the idea here was just to get a plausible first handle on this. And to do this, we looked at existing few degree squared fields where the angular clustering of these galaxies have been measured. So for Lyman alpha emitters, the Odin survey, and for Lyman break galaxies, this older CARS survey. And what we did is we got the linear bias and number density from the angular clustering from these surveys, from the observed W of theta, and then said, let's build some simulated selections that match these two numbers and then look at their nonlinear biases. So that's what we did using this field level machinery that allows us to cancel sample variance when measuring bias parameters at the field level from these simulations. Okay, so here is just an overview of the selection that we had for LAEs and LBGs in two different simulations that we used, the Millennium TNG and Astrid simulations. So Millennium TNG on top and Astrid on the bottom. Like I said before, the LBGs are, you can think sort of analogous to LRGs, except they're star forming. On the bottom axis is the stellar mass, and here is the specific star formation rate. So star formation rate divided by mass. And here are the LBGs at high stellar mass, and then the LAEs occupy a wider range of stellar mass with our selection here. We perform this selection using the hydro properties because there's no realistic colors or spectra, but people from the astrophysical literature have worked backwards from the observed spectra and photometry into stellar mass and star formation rates and for these galaxies. So that's, I can say a little bit more about that if you're interested in how we did that. But we used stellar mass, star formation rate, and metallicity to make these cuts. And for the field level machinery, we've had a few nice talks about the field level here already. But we used this transfer function tooling that was described in Misha's talk, where we have a cubic bias model with the shifted operators and some orthogonalization of the operators. And in front of each of these guys, we have a transfer function as a function of k and mu for redshift space. And we're looking for just the K-max results I'm going to show you at the error power spectrum and seeing when the power spectrum of the residual starts to have significant K or mu dependence for an indication of where the model is breaking down. So probably I just wanted to give you a quick takeaway since this is a short talk. We start to see significant mu dependence this is for the LAEs and this is the LBGs around K-max of 0.2 to 0.3 for these two different populations. And actually the K-max can be much higher depending on the selection, depending on the simulation. This here I'm showing you for Astrid, the results here. In purple, we have different mu bins, and black is the real space error power spectrum. And the stochastic contributions from fingers of God are what are sourcing the scale dependence in the error power spectrum and limiting our effective K-max. But the story here is basically that the K-max reach is similar to what we're getting at low redshift, in fact, even a little bit better, and it could be much better depending on your assumptions that go into your simulation and the selection. And we should look at this more with more realistic simulated galaxies. Some people have started building some empirical models that could improve upon what we did here in a paper that came out a couple months ago. You could imagine building simulation-based priors from this kind of methodology if you had an AV that you trusted for these galaxies. And finally, you might be able to use these sort of perturbative mocks for testing pipelines because they're very cheap to generate. So I'll wrap up here. Any questions, please?
Thanks a lot, Jeremy. Two questions. So very good question about the flatness of this noise. Maybe you can go back to the.
I can see it. Okay.
So why does it need to be flat? And also, is there anything that you can learn from the power that you do get if you or from the slope that you get? If you see where it becomes scale dependent, I mean, in principle, the noise doesn't have to be flat, right? In this EFT sort of framework, but that's kind of a unique question.
I mean, the scale dependence should go something like flat and then k squared and then k squared mu squared, right? And we're talking about in particular where it deviates from that behavior. Yeah. I can show you exactly how we quantified these k maxes. It's in the paper, but we can talk about it.
I mean, there is that observable combination of multiples that mimics, let's say, the real space power spectrum that is less sensitive to figure of God. So I was wondering if you would do this exercise with the High-redshift sources, if this would allow you to go at higher scales.
Sure. Yeah, I'm not exactly sure about the details of what you're referencing, but we could definitely do that. We could,
It's not much, but it's really-
right, sorry.
I think it's like-
Yeah.
Now, then I understand.
Really depth of P. So it's both the perpendicular ones and the radial ones.
No, the point is that you should, let's say, you should not take the modes that make you, say, non-perturbative too soon in order to get to IRK. That's the thing. At least the way I understand. So this level, in the sense of taking the field level, makes your non-perturbative scale to hit you sooner.
Just to clarify, we're not suggesting doing the analysis at the field level here. We're just trying to get an idea of what the bias parameters are and then
Yeah.
go work at the level of the power spectrum.
So, actually, I think that one of the first to propose it, we should. No, if I'm not mistaken.
No, sure, but we can talk about it.
Yeah, okay, let's do that.
Do you have a theoretical understanding of the separator of the shot noise in terms of exclusion radius and stuff like that?
We have not looked at it, but these are very small galaxies. I mean, we're at higher K, but these are even smaller galaxies than you would usually think about for this exclusion radius.
Something.
It's a bit complicated. The satellite fractions are very high for example, the LAEs is like 30% satellite fraction, one of these simulations. So yeah, it could be something coming from the larger halos exhibiting exclusion, but between the satellites and each of the halos. Yeah, we didn't look at that. We could look at that.
Can I also ask you, because you said you're limited by use of God,
Mhm.
but I remember LPG, the fraction of satellite was like 3%, and there's all kind of. So I can see that for LAEs, you have the lots of satellites, but from HSC data, when you were looking at this, the fraction was small. Okay, so these are actually large.
Yeah, it's 10%,
This is
12%. This is in simulations, right? Yeah. But
That's large.
yeah.
Okay, if there are no other comments, let's thank Jamie.